rearrangements of the infinite series. We know that for the finite series, such as a sub 1 plus a sub 2 plus a sub 3, we can rearrange the terms by permuting the order of the terms, and the sum is still the same. What about the infinite series? If we have a convergent series, after we rearrange the terms, will we still get the convergent series? And if it is, will the sum be the same? Consider the alternating harmonic series, where we know that it is convergent by the alternating series test. And so its sum is a finite number s. This series is 1 minus 1/2 plus 1/3 minus 1/4. The even terms are negative and the odd terms are positive. We're going to rearrange these series by starting with one positive number and two negative numbers. So 1 minus 1/2 minus 1/4 plus 1/3 minus 1/6 minus 1/8 plus 1/5 minus, and so on. Remember that the odd terms are positive and the even terms are negative. We then simplify the two consecutive positive and negative terms to get 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus, and so on. And then we factor out 1/2. We end up with 1/2 times the quantity 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. But the series inside the parentheses is the original series. And if the original series converts to the sum s, then we end up with 1/2 s. What we have here is the finite number s equals 1/2 s. So therefore, s must be 0. But we know that this is not true because for any convergent alternating series, the sum of the first even terms is less than the entire sum. And we know that s sub 2 is already 1/2, and so the sum has to be positive, which is clearly a contradiction. This means the operation that is valid for the finite sum is not necessarily true for the infinite sum. And so we start with the sequence a sub n to form the series, and we form a new series using b sub n. It is true that b sub n contains all of the terms in the sequence a sub n. And there is a one-to-one correspondence as well. For example, the term a sub 1, which is 1, is mapped to b sub 1. The term a sub 3, 1/3, is mapped to b sub 4, which is 1/3. The term a sub 5 is mapped to b sub 7. The second term is mapped to b sub 2. A sub 6 is mapped to b sub 5. And a sub 10 is mapped to b sub 8. And so on. And so we see that there is a one-to-one correspondence for each of the a sub n term. We can map it into a distinct b sub n term. Recall that the sum of an infinite series is the limits of the partial sums. So because of the limit, there is no reason why we assume the sum of the series a sub n is the same as the sum of the series b sub n, because a sub I is not the same as b sub I. For example, in our example, we see that a sub 3 is not the same as b sub 3. The result of the rearrangement. If the series a sub n converges but does not converge absolutely, that is, the series a sub n converges to a finite number, but the series of the absolute values diverge, then for any number r at all, there is a rearrangement b sub n of a sub n such that the sum of b sub n equals r. And so this is how bad conditionally convergent series are. Potentially, we can rearrange the series to get any number we want. For absolutely convergent, if the series a sub n converges absolutely, that is, the series converges and the series of the absolute value also converges. And if b sub n is any rearrangement of a sub n, then the series b sub n also converges absolutely, and the sum of a sub n equals the sum of b sub n as n go from 1 to infinity. And so with absolute convergent series, the sum remains the same after the rearrangement.